I'm going to show how to derive the buoyancy equation and prove Archimedes' principle in this video. I'll start with the main concept. Imagine a room like a big kid's ball playroom, but it's full of marbles that are all slicked up with oil so they can slide past each other like a fluid or a liquid. So you have a couple of boards right here on each side blocking out those marbles. As soon as you yank up those boards, those marbles are going to want to rush in and fill that void right there so that the top is level, as if it's the top of a swimming pool or just the surface of water. If you have any lighter objects in here, like a piece of styrofoam or something, and you have perfectly frictionless fluid here, like the marbles, for example, they're going to slide underneath it because gravity pushes them down harder, and they're going to push it up. In reality, if you're dealing with something like marbles or sand that's heavy, then they'll just end up covering the object up. But there's some neat science toys where basically you just get like a box of sand and you could bury some styrofoam underneath all the sand. But as you shake that box and everything's able to move around, then all the little styrofoam pieces or foam pieces will get pushed up to the top as the sand gets pushed down to the bottom. So it basically gives you a demonstration of buoyancy in a box. The concept of fluid wanting to fill a void is called horror vacui, which is another way of saying nature abhors a vacuum. That horror vacui is just a Latin term. There's a Wikipedia article on it. And right here, Archimedes' principle is related. If you put any object in a fluid, the mass of that object will displace the same mass of fluid. So if this is a tub full of water and that water is all the way at the surface, you put in a little toy boat or a block of wood or whatever, it'll displace so much water. That water can pour out the side here and you can catch it in a bucket. You could then weigh that water and know the weight of the object. Or if you want to be a little more sophisticated about it, then dumping water all over the floor or something, you could just have increments or a scale on the side of your tub right here. And as that water goes up, measure the volume, use the density, and you'll have the mass. And that's simply because density times volume equals your mass. I think the idea of volume, replacing volume, is logical. So if you put in, say, a big block of wood that is 1 liter in volume, it'll dump out 1 liter of water. But the idea of mass replacing the mass of an object, replacing the mass of water, I think that was a little more difficult to understand and prove. By the way, that only works for things that are buoyant, which means they float. If you go chisel off a piece of a neutron star, so you have 1 cubic centimeter of it, and it weighs several hundred or several thousand tons, and you put that piece of a neutron star in the water, it'll come down. So say you have a scale right here, and that tank of water sits on a scale. That piece of the neutron star will displace almost no volume, but it'll make the numbers on that scale go way up. And compare that to a boat or something that floats. As long as that water is at the very top of the tub right there, whatever you put in will cause that certain amount of mass of water to be displaced, so the scale will not change. And I'll show the proofs for all that. First off, a whole bunch of basic equations. I'm going to fly through these so you can pause the video if you want to look at them. We got a column of water here that is 4 cubic centimeters. So centimeter cubed is the same thing as cc, which is the same thing as a milliliter. Density of water, 1 gram per cubic centimeter. Height times density equals force. So if you're right there at the bottom, 4 centimeters deep, you take your height, which is 4 centimeters, times the density, 1 gram per cubic centimeter. Notice this centimeter right here will cancel out. You'll be left with centimeters squared here. You get 4 grams per square centimeter, and that is your pressure. And I forgot to mention this is force in, say, kilograms of force or grams of force. So we did not add the acceleration of gravity yet to turn that into newtons. And right here, I just said density times volume gives you your mass, because density is mass per volume times volume. The volumes cancel. You just end up with mass. And next page. So as I showed here, height times density equals your force in either grams or kilograms or whatever. So add acceleration from gravity to get your pressure. HdG equals pressure. Height would be, in this case, I'll call it 4 meters. Density of water, 1,000 kilograms per cubic meter, times acceleration of gravity, 10 meters per second squared. That equals your pressure. Let's see what happens to our units. This meter cancels out. You end up with meters squared right here. Now we have mass times acceleration per area. So that's mass times acceleration equals force. That becomes force per area, and that equals your pressure. In this case, newtons per meter, because we have kilograms, times meters per second squared. Also notice here I'm avoiding lowercase a, which typically means acceleration, and instead I'm using g for acceleration from gravity. That way I can use a capital A for area. Force per area equals your pressure. Like right here, we have our newtons per square meter. That means pressure times area equals your force. And that breaks down to force per area is your pressure times area. The areas cancel, you get force. And next page. All right, HDG equals pressure. Multiply pressure times area to get your force. So we have HDGA to get our force. HDGA. Let's look at our units. In this case, a little tricky here. M means meters and not mass. So sometimes you gotta think about it to keep your units straight. Height will be in meters, density, kilograms per meter cubed. Acceleration, let's see, G is meters per second squared, and then area is meters squared. So what we have here is this meter cancels, that becomes meters squared. If this is meters squared, that will cancel with that meter squared. We end up with kilograms times acceleration, so we end up with mass times acceleration, which equals our force. I'll use this one to prove the Archimedes principle and derive the buoyancy equation. So just remember HDGA equals your force, also equals mass times acceleration. I got a little sidetracked on this part here. I went off the rails a little bit, which happens sometimes when I'm learning this stuff and just trying to figure everything out. I thought that the volume would matter here, but I don't need to derive volume. Take your HDGA here, height times area equals the volume. So you end up with density times acceleration of gravity times volume also equals your force. Notice here again, the units will cancel. Meter cubed, you end up with mass times acceleration equals force. Again, I'm just showing that because I thought it was necessary at first, but it's not. You can leave this step out of volume and just say that HDGA equals force. Here's the simplest proof I came up with. By the way, I came up with a couple of proofs for Archimedes' principle. Here's the simplest one. Just have a big test tube right here floating in the water. Put a rock or something in the bottom here to give it some ballast so it doesn't tip over. That test tube is going to sink down in the water to a certain depth. Let's say 4 centimeters right here. So 4 cubic centimeters, it'll fall down to the 4 area. And so this gives this whole area right here, the density from the surface of the water down. This density will be 4 grams. So say this rock plus the test tube or whatever all equals 4 grams. And it's occupying 4 cubic centimeters. 4 grams per 4 cubic centimeters, 1 gram per cubic centimeter. That is the density of water. Notice right here in this thought experiment, everything in this tube right here from the surface of the water down to the object or the bottom of the tube has to have the same density of water, which means it has to be neutrally buoyant. And this is why. Everything here weighs 4 grams and it's occupying 4 cc's. So thus it has the same density of water from the surface of the water down. Now imagine pushing up on this object right here. So now the water level goes to 3. Now we'll have 4 grams per 3 cubic centimeters. Then that means everything becomes more dense than water, and thus it'll have to fall. Likewise, take your fingers here, pull that down so that that water level goes up to 5. Now we have 4 grams per 5 cubic centimeters. It is now less dense than water. And with the way density works, just like a bunch of marbles falling in to fill a void, if this is less dense than water, then all the water has to rush underneath and push it up. The equation here, mass per volume equals your density. That means density per volume equals your mass. So this is like, say, mass per volume times volume, and thus the volumes cancel. You end up with just mass. The reason this matters is, what I said here is the density of this object. must equal the density of the water. And so right here, the density of the object is the mass divided by the volume must equal the mass of the water that it displaces divided by its volume. The volume is the same in both cases, 4 cubic centimeters right there. Since the volumes are identical, they cancel. That means the mass of the object must equal the mass of the water, which shows that the object will always displace the same mass of water as itself, thus proving Archimedes' principle. Also, you can use this method to weigh something. It's called hydrostatic weighing. I just looked it up. So if you don't know the weight of something, you put it in a big tube like this and see what the volume is that it takes up. So here you can see it takes up 4 cubic centimeters of water. Volume times density equals the mass. Then that will give you the mass of the object as 4 grams. And here's the buoyancy equation right here. Take the density of the gas in your balloon minus the density of the air, or vice versa. Multiply that by the volume of your balloon times acceleration from gravity, and you get your force. And I'll show how to derive that. Here's another schematic or another diagram. We got a rectangular balloon here floating. Let's see, so the volume of air above this balloon pushing down on it will be called V1. The balloon itself will be V2, or volume 2. The height of the air column above it will be H1 for height. The height of the balloon here will be H2. What got me interested into looking into this was I got curious about pressure differentials, how there's a certain amount of pressure pushing down on the balloon from the top, a certain amount of pressure pushing up underneath. So I wanted to look into that. Because also if you take this, say it's a rectangular balloon that's laying flat, you turn it up sideways or on edge, you have less surface area underneath here for the air molecules to get underneath and push up, yet it has the same buoyancy with less area. You're also going to have less area right here for the pressure from the air column on top pushing down on it, so you'll have less pressure on the bottom and less pressure on the top. But the next few pages here, I'm going to look into the math of that. But in the end, I guess I should say I was a little bit curious as to why right here, for example, with the balloon laying flat, you have more area, so it seems like you should have more lift compared to if the balloon is vertical like that. But I think everybody knows if you're holding onto a helium balloon, it has the same lifting force regardless of its orientation. All right, next page. These next couple pages I'm going to show come from this picture right here. Imagine you're at the bottom of this water column. You're going to be under that same amount of pressure and force from HDGA that I just showed. So this same water column could be right here pushing down. And we start with getting the height of this object right here. So what we have here is this force pushing up on this object, providing buoyancy. That's pressure times area, and that pressure turns into HDG. Bring down the area, you got HDGA as the force pushing up on this. And that's because you have this whole column of water pushing down right here exerting pressure, and pressure exerts a force in all directions, which means it's going to be exerting an upward force as well. So this HDGA will represent the force, but it also represents the mass pushing up on it, because force is mass times acceleration. And it also represents the amount of volume pushing up on it. We could actually show this by taking the same HDGA equation and flip this whole thing upside down. So now instead of having that mass of fluid pushing up on it, the mass of fluid will be pushing down on it. So now we have a force downward, which is pressure times area, HDGA. We have instead of the height of our object, we have the same height, but now it's the height of the water column. You can go through the intermediate step to get volume if you want to, but in the end, you end up with mass times acceleration from gravity. So you end up with force pushing down on that. And the way we get this force from this diagram right here was the HDGA, which will have the exact same numbers on this page as they will on this page. So whether that pressure is pushing up or down, it's the same equation from the same displaced mass of fluid. So I just said right here, since we're dealing with the same mass, therefore the mass of fluid that the object displaces is what causes the buoyancy, which is Archimedes' principle, and also leads to the buoyancy equation. On this next page, I'm just going to show that the air pressure pushing down on our object or that same force, will be canceled out by also pushing up on the object. Here's the diagram here. I just said the pressure from H1 pushes up and down on this object, whether it's like a balloon or a piston. Imagine you have a piston in a cylinder here. You got a volume of gas with pressure pushing down on it, creating a downward force on this balloon or piston. But we can actually take the same diagram, have a hose, such as like a pneumatic hose or a hydraulic hose, connect the top to the bottom. Therefore, whatever pressure you have pushing down on the top will also be the same pressure pushing up from the bottom. Thus, this height one right here, so this whole column of air and that whole volume of air and mass of air pushing down on it will be canceled out, because you can actually just remove this hose and you'll have infinite area all around this object for that gas to come down and push up underneath. I just showed the same equation right here, which I really didn't need to, but I'm going to show this algebraically as well, how this mass of air, or this force from this air pressure, will actually be canceled out. Let's first look at our forces pushing down on our object right here. We're going to have the force of the object pushing down, which is the block or the helium balloon. That force is going to equal mass of the object times acceleration of gravity, plus we have the pressure pushing down on this, and that pressure times the area is going to be your HDGA. Go through the algebra right here, and we end up with the force pushing down equals the mass of the object times gravity, plus M1, which is the mass of the air that occupies volume 1, that is also height 1, so times gravity. So it's all the air right here, that column of air pushing down on it, the object, plus the force of the object itself pushing down. The next page, I'll show the force pushing up. All right, so here's the force pushing up. It's your pressure times your area. Right here, we have something pushing up on this, say, a helium balloon here. Remember that pressure comes from the mass that's pushing up on it, which comes from the height right here. And also remember, the initial height here will actually be canceled out, because we'll have a certain amount of volume or mass pushing down on this, volume 1. And that same mass is going to come underneath and push up as well, so it'll be canceled out. So it'll be pushing both down and up, and I'll show that algebraically. So force pushing up, pressure times area, that's your HDGA, but we have to use both H's, H1 and H2. So just do DAG H1 plus DAG H2 right there. Both of these turn into mass times acceleration. So here we have M1G. That M1 is the mass of the air column from height 1, and then M2G is the mass of the air column from height 2. So the reason I showed all those previous equations and diagrams is to show that the pressure here at the bottom is related to the entire height, and the upward force on this object is related to the height of the object itself. So now we can set our downward force equal to our upward force. Downward force is the mass of the object times gravity, plus the mass of the air column above it times gravity, that's M1. The upward force will be the mass of the air column above it times gravity, plus mass 2, which comes from height 2 right there, and that is the mass of air that it displaces, or mass of fluid. You can see M1G cancels out on both sides. We end up with the mass of the object equaling the mass of the air that it displaces, which is Archimedes' principle. And I just said here, M sub O is the mass of the object, M sub 2 is the mass of the volume of air that it displaces. So I guess I should say mass and volume. Notice this right here is Archimedes' principle. The mass of the object right here will displace the same mass of fluid, and that is what causes the buoyancy force. Notice this is just a more complicated example, because we have our item floating here like a balloon floating well underneath the surface. So we have that column of air that I label as volume 1 pushing down on it. But if we look at the simpler example that I showed at the beginning, you can see here that it's the height of the object itself that creates the mass. Or I should say that it's the height of the object itself that's related to the mass that is displaced, and that same mass is what causes the buoyancy by creating a force pushing up on it. Next up, I'm going to subtract one force from the other force to get a net force to find out how much force we have pushing up or pushing down. Right here, I got force pushing down minus force pushing up gives you your net force. The force pushing down was the mass of the object times gravity. The force pushing up is the mass of fluid that object displaces, so it's m2 times gravity. Pull out your g, then you have mass of object minus mass of fluid it displaces. It would be difficult to weigh the mass of air inside of a balloon or the mass of air that is displaced from it, but we do know those densities, so let's turn masses into density. Mass of object over volume minus mass of fluid it displaces over volume, but then multiply both of that by volume, so we end up with the same equation. Notice here the volumes will cancel out, then we'll just end up with mass minus mass times g, mass minus mass times g, or force minus force equals net force. And here, mass per volume is your density, so we end up with density 1 minus density 2 times the volume of the balloon or the object times acceleration from gravity gives you your net force. Also, if you're just trying to find out how much a balloon can lift, like how many kilograms, you can just eliminate that g right there, because for example, if you use it, you're going to get a net force, but then you have to take that net force, divide it by g to get your mass that you can lift with a balloon. This equation is interesting because you can interpret it 3 different ways. You could say you're taking force minus force, or you could say you're taking mass minus mass, or you can say you're taking density minus density, and they sound like 3 separate equations, but it's actually all the same equation. Also, to notice, if you have decreased gravity, this will give you a decrease of net force or decreased lifting force, but you can also still lift the same amount of mass. And that is because gravity has a linear relationship with force, so as gravity goes up or down, so does force. So you can multiply gravity by 2 or 5, or you could divide it by 2 or 5, and that'll decrease the force the same amount, but notice your mass will be untouched. Also notice for this equation, something doesn't have to float in order to use it. You could have a rock sitting on the ground, and just take the density of the rock minus the density of the air times the volume of the rock times gravity, and that will give you the upward buoyancy on that rock. So that rock will weigh slightly less here on Earth with an atmosphere compared to if you put that rock, say, on the moon with no atmosphere. And that same rock would weigh even less if you put it at the bottom of a swimming pool. You could plug in some numbers here just to see what would happen. Take the density of a rock, say about 3,000 kilograms per cubic meter. Google said limestone was around 2,500 or 3,000 kilograms per cubic meter. Water is about 1,000 kgs per cubic meter. Air is about 1 kilogram per cubic meter. If our volume is just 1 cubic meter, then that simplifies the equation because we don't have to calculate the 1. So for example, if we just have a rock sitting on the ground in the air, then we could take that 3,000 kilograms per cubic meter minus 1 kilogram per cubic meter. 3,000 minus 1 would be 2,999. So basically on a scale that weighs kilograms, we don't even have to use the G either. So this means if you were to have this 3,000 kilogram rock on the moon and it's 1 cubic meter, it would weigh 3,000 kilograms on the moon, but it would weigh 2,999 kilograms here on Earth because we subtracted that air density right there of 1. And if you want to put that rock underwater, you just take 3,000 minus 1,000. That gives you 2,000. So that means that 3,000 kilogram rock would just register as 2,000 kilograms at the bottom of a swimming pool. Also, I've noticed people like spreading all sorts of crazy myths. So here's a good one. Someone could say that a rock would weigh a lot more if it was at the bottom of the ocean compared to if it was at the bottom of the shallow end of a swimming pool. And they could say that's because of the huge water column that's pushing down on top of it. But if you notice in this buoyancy equation here, depth is not taken into account, or depth of fluid does not matter. And as I previously showed, the force from that column of fluid on top of the object will be canceled out from that same force pushing on the bottom of the object. So whether that rock is at the say 1 meter deep in the shallow end of a swimming pool, or if it's 1,000 meters deep at the bottom of the ocean, it would still weigh the same if you put it on a scale. So all sorts of interesting tangents here.